Welcome to the last week of multivariable calculus. This is lecture 24. It's a big one, flux integrals and the divergence theorem. All right, it's one of our four big theorems of vector calculus. The first one, 3D. So our objectives are first to compute surface integrals of a vector field. All right, so far we've done a bunch of surface integrals. Some were just surface area, right, which is really just integrating the function 1 over our surface. Then we integrated other scalar valued functions over our surface. And finally, we arrive at the most complex ones, but in some ways the most beautiful integrals of a vector field. I don't say over a surface, I typically say through a surface. You'll see why. But sometimes people say across a surface. It's a little ambiguous. Anyway, we'll get to those kinds of surface integrals in a minute. And then we're going to get to the divergence theorem. Right, which is one of the big theorems. Again, we really want to know what its statements. We're going to describe it as a conservation law. I'll get into what I mean by that, and then we can use it to compute flux. We'll see that in some examples in class. Here, we really just want to get to the theory in this video. So before we talk about flux integrals, really, we got to talk about orientation, particularly orientation of a surface. So you recall that curves are orientable. We orient a curve that go along one way when you compute a line integral, and you get an answer for a line integral of a vector field. And if you reverse the orientation, in other words, go backwards, you get the negative answer. So something similar happens with surfaces. Here we need to orient them, although it's not as obvious what to do. Right, here's my surface there. What do I mean by orienting the surface? Well, in three-dimensional space, I don't mean pointing which direction does it point in. I really just mean which direction is up. All right, so it's a choice of a unit normal vector. So your typical surface has two sides, of course. And so a choice of orientation is kind of just like which way is up, and I should put up in quotes because I don't really literally mean up. I just need some way to say which way is the positive direction, right, from this surface. There are exactly two choices, right, for a surface. So think of a unit normal vector. We're in 2 dimensions. Right? There's only one line, normal meaning orthogonal to the surface there. And an orientation is a continuous choice of normal vector. So at every point along your surface, you choose the normal vector. So I'm choosing this way, right, as my positive orientation for my positive direction for my surface. So the orientation is this choice. There's exactly 2 choices of orientation for any surface here. It's the kind of the direction through the surface, if you like. Now, from the practical matter, certainly for this class, what does that mean? You just want to arrange your parameterization, which that's R of uv that we use in computing all surface integrals here. You just want to arrange it in such a way so that RU cross RV, right, that's that special vector, points in the direction you want, right, in the direction of n, your unit normal vector. That you want for your given application. And the whole point of the orientation is so that people, you convey what the orientation is, and then a computation that results in a number, people know what direction it's associated with. So you choose your orientation so that RU cross RV lines up with that choice. And the neat thing is, since there are exactly 2 choices, if you get it wrong, you pick your parameterization and you have the wrong RU cross RV, simply switch U and V. Right? Just literally name one U and the other one V and switch them. The surface won't change the number of points there, but your choice of normal vector will be exactly the opposite direction, right? Because a cross product, right, is anti-commutative. All right, so here's some common examples, right? Let's orient the graph of a function. So that means, right, so I've got a graph of a function. That was one of the kinds of surfaces that we talked about. A typical way to orient it, not required, but a typical way to orient it is so-called upward. And upward in quotes, you'll see what I mean. Right. Here, so here's the graph of a function, and upward means mostly upward. And we can say what we mean more literally here, right? How does that work? Well, when I choose this parameterization, I already know that my surface is oriented upward. Here's how here's how I know that. I can take out my pen here. If I start computing RU cross RV, Here, I'm only going to do a piece of this here. What do? It's a cross product. I'm going to do the old matrix notation here. I know that RU is going to be 1, 0, something right here. And then RV is going to be 0, 1, something else right there. And the reason I don't care about the somethings for this demonstration is that when I evaluate this guy, well, in the X and Y, I don't know, I get some nonsense there. But in the Z component, I'm guaranteed to get 1 if I've parameterized things this way. Right? Notice for the K component of the cross product, it's just 1 times 1 minus 0. Right? So that's always going to be 1. In other words, the K component of my normal vector here will always point upward. Right? If I orient it U for first component, V for the second component, and so on. Right? So that's a typical way to orient the graph of a function. What about surfaces of rotation? Well, there we tend to have a notion not necessarily of upward, but outward. Right, so here's a little cone that I've parameterized in the usual way. Right, so notice that it goes along the y-axis now. Right, that's the axis of rotation, and this thing moves around around the y-axis. So I see cosine, sine in the xz plane. Right, so that's kind of counterclockwise, if you like, in the xz plane. And the result of that, right, is normal vectors that I'd say point outward. Right, here's the picture. And there's some notion of outward versus inward for a cone. Not for every surface. Right? What's the outside of this surface? That's not well defined. But for a cone, outward means something, and so you set up your parameterization so that when you compute RU cross RV, it lines up with that. It's a little hard to describe orientation, but it turns out not to be a big deal. And when we dive into the examples, we'll get into that. Although it is important to recognize there are some strange surfaces out there. Right? One you probably have heard of is the Mobius strip. Right? Here's its parameterization. If you like, perfectly parameterizable surface. I can take this, I can compute its surface area, but here's what it looks like. Right? You recall, it's a loop with a twist in it. And right, that has a twist in it means there is no outside versus inside. Any choice of normal vector can't be continuously across the whole surface. If you just take your eye and imagine an arrow pointing outward, right, on the edge here, and then imagine continuing the choice outward over here. Well, at some point it flips, right? To be pointing inward. Or do I have maybe I have too many twists on this guy here, actually. But a typical Mobius strip, it ends up pointing inward here, and that's a contradiction. So there are no such thing as non-orientable curves. There are such things as non-orientable surfaces. We'll avoid them in any real example in this class, but just be aware. Right? Geometry, when you get more dimensions, strange things do happen. Okay, but let's assume we're going to work with orientable surfaces for the rest of this talk. So what can you do with them? Well, we can compute flux integrals. Right? This is what I was saying. This is our last kind of surface integral. It's the surface integral of a vector field. Right? So how can we add up a vector field? Well, basically, there's only one way of doing it. So let's look at the ingredients quickly to what a surface integral of a vector field is, otherwise known as a flux integral. This is the notation we use. And so, again, we ask where, what, and how. The where is, again, 2D surface in R3. It's going to have a parameterization. Right? So R takes this D is a two-dimensional region. It maps it into R3 space. Right? You think of like embedding a surface like this in three-dimensional space. Here, it's going to be orientable though. All right, so no Mobius strips, no Klein bottles, no weird stuff. Here, so that's why we have a choice of n. Right, is our unit normal vector. So it's that choice of orientation here. The what is a vector field F defined in R3, right, in the ambient space. Right? I'm going to often think of it as a flow of some fluid, but you can write a velocity field of some fluid, but it's just some vector field, right? That's defined everywhere. And the how is we're going to measure how much that vector field points through the surface. So just like in with curves, typically we measure vector fields along the curve, right? There, because you could just do a dot product with the tangent vector. But in 2 dimensions, we had that special case where we checked the vector field perpendicular to the curve, right? And we called that flux. Well, this is exactly the analogous thing in 3 dimensions. But now we have a surface right here, and at every point in space, we have got some vector field, right, pointing somewhere. And so we're going to measure how much that vector field lines up with the normal to the surface. I wish I had one more hand, one more pencil to demonstrate. So how do you compute that, right? In some ways, the most important feature of this, once you recognize what kind of thing you have, a flux integral, a surface, a vector field, how much does it flow through? What you do is based on this definition here, I'm going to add up the dot product of the vector field with the normal vector and then integrate that with respect to surface area. So these are equivalent notations for the same computation. I've got the surface omega, the vector field f, and I'm measuring how much it points through the surface. So another way to say the same thing is I've got my surface omega, I've got the vector field f, I dot it with the unit normal vector to my surface, and then I integrate that scalar with respect to surface area. Okay, so these two are 2 ways of saying the same thing. But how do we actually compute it? Well, this thing on the right, I actually know how to define. Right? I've got a parameterization for my surface. So I've got a function r that takes d onto my surface, omega, in 3-dimensional space. I evaluate the vector field I find at each point. So that's this term here, right? So that's a vector in R3 now. I'm going to dot it with the unit normal vector. Right? So notice that I've got the normal vector I defined here divided by its length. I missed a bold on the r here, but recognize this whole thing as n. And then to evaluate to integrate with respect to surface area, right, recall, we take the magnitude of RU cross RV. But you'll notice, right, if you haven't already, that exactly we get cancellation between these 2 terms. And this becomes quite a nice computation altogether here. Right. Scroll down. Right. Things cancel, and we get this really nice expression at the bottom. So when I want to do a flux integral of a vector field through a surface, across the surface, here, I take my parameterization, I evaluate the vector field, I dot it with RU cross RV. Right? And so that gives me one scalar. It's a complicated expression, but I get a scalar when I'm done with it. The cross product gives me a vector. I dot it with the vector field. That gives me a scalar, and I can add that up all over as a plain old double integral in u and v coordinates. So a surface integral becomes a uv double integral. Let's look at that integrand, right, to figure out what's going on. Why am I calling this a flux? Why am I saying flow through, that kind of thing? So if we zoom in on one of these terms, right? I said this thing's a scalar, but remember where it comes from. So I've got a picture of my surface here. I can rotate it a little bit so you can see. Right, there's my surface down there. And then remember that RU and RV, right, kind of are tangent to my surface. So together they define a parallelogram tangent to the surface, right? A piece of the tangent plane there. The blue arrow here represents the vector field F. Right, so I've got my 2 tangent vectors, RU and RV. Right? And they form a parallelogram, and remember that the length of the cross product is the area of that parallelogram there. And then I dot it with the vector field I find at that point, so that's what F is. And I get a triple product, if you remember that term from early in the semester. In fact, that gives me a volume, really a signed volume here. So depending on my orientation, I'll get a positive or negative number out of this guy. It's positive when the vector field aligns up, right, points in the same direction as RU cross RV. Right? In other words, F points in the same direction as the orientation. You get a positive number, right, through there. And I get a volume of this parallelepiped there. So what does that mean? When is it big? So it's big when f is big, when it points through the surface in the direction perpendicular to the surface. If f is parallel to the surface, I'm going to get 0 from this dot product. Right? I'm going to add 0 volume of this parallel pipe bed, or another way to see it is that this RU cross RV is normal to the surface. If f is parallel to the surface, they're at right angles, you get 0 out of that. So the reason it's called a flux, right, Latin for flow, integral, is we're kind of imagining if f is the velocity of some fluid here, what I get, so that would be like meters per second. What I get when I integrate all this up is meters per second times meters squared, right? That'd be like meters cubed per second, right? So it's a volume per second, how much flows through the surface at any given second. And of course, I'm going to take a limit somewhere, right? This picture isn't the right one. I'm going to chop this thing up into finer and finer pieces. There, I've chopped it into 4 pieces and done this on each one, right? Which makes it a little more accurate. And then I can chop it up into 9 and then 16 pieces here. And you see that as I take a limit, of course, right, you really do get a volume coming through right here. So you're adding up all the little bits of flow through this surface, right? A bunch of little parallel puppets. Okay, so that's the thing you're adding up. It's why we call this thing a flux, and hopefully make some geometric sense. Here's a quick, really silly example. Right? It's kind of the analogy I think of with a flux integral. The things I picture when I have a flux integral here is a flowing stream. Right? Its velocity is what signifies the vector field f. So I think of f as describing some flow of some stream here. And then my surface omega, I think of it as a fishing net. Right? How does that work? A fishing net is typically a 2-dimensional surface, and of course it's permeable. The water flows through it right here. So right, how do you fish with a fishing net? Well, what you hope is that the stream flows through it. Right? Water goes through your net. The fish stay, of course, in the net there, and that's your catch there. So you want to increase flux. Right? The more flux you have, the more river goes through your net, the more fish you catch. So here's the question. I've got 2 choices for how to stick my net into the river. Which one is going to catch more fish? Which one's going to have the higher flux? A piece of the plane y equals 0 or a piece of the plane x equals 0? So the flow is straight, constant I direction. So I've got this stream steadily flowing in the I direction down this way. The first surface, you see it oriented here. Am I going to catch any fish there? Well, I hope you think no. Right, the flow is all in the I direction, right? That's perpendicular to the normal vector to my surface, right? It's parallel to the surface, so the flux is going to be 0. Nothing is flowing through this fishing net. Of course, if I turn it a little bit, right, in such a simple case, this is a much more sensible way to fish the stream now, right? Much more flow through my surface. The normal vector of the surface aligns with the vector field. I get a big number, right? Everything coming through this net will get caught. All right. Here. So it's a good analogy to think of. And if you do something in between here, right? Of course, the flux is going to be somewhere in between. The surface area hasn't changed here, but the amount going through has. Right? If I turn the perspective a little bit here, you can see that that's the case. Right? If I don't make it all the way parallel here, right, now the dot product between the normal vector and the vector field is going to be smaller. Right? There's going to be more of an angle between them. And it makes sense, right? It's like I'm blocking less of the river. There's less flow through it. Okay. Now, it's a good analogy. Fishing net, right? Stream, not perfect. Don't take it too literally. For one thing, right? If you reverse the orientation and flip your net out, fish don't suddenly come flying out of it, right? Whereas in a flux integral, if you reverse the orientation, you get the negative number. Okay, so what are we going to do with these flux integrals? Well, now we get to the big theorem. It's called the divergence theorem, so it's probably worth reminding you what the divergence is. You start with a vector field, P, Q, and R being its 3 components. The divergence we represent as del dot f, right? Del being the funny operator. It's like a vector with differential operators in each component. But here's the formula, right? It's the x derivative of the first component, the y derivative of the second, the z derivative of the third. Px plus qy plus rz. Right? And remember, it measures to which the degree to which a vector field is expanding or spreading out. Right? When you have a source field, right, like x, y, z, of course, that divergence is pointing away. Right? It's like flows being produced, and exactly right the opposite for a negative, right, negative flow, something compressing toward the origin has negative divergence. And there are lots of interesting examples of things with zero divergence, which still have interesting flows. It's just that like volumes aren't changing. It's not compressing, right, or expanding in the net. So that's what divergence is, which hints at right another big theorem. Right? This is exactly a three-dimensional analog of this one form of Green's theorem, which remember that happened in a plane. There you had a loop, right, and the solid region D, and then its boundary there. And if I integrated f dot dn, so that's the flow of my vector field through the surface, through the loop, right, out of the loop, right there, it turned out to be the double integral of this divergence on the inside. So that's what Green's theorem said. So it said total flux through the boundary was the integral of the divergence on the inside. And the three-dimensional version basically says the same thing. Now, though, I've got a solid region E, so it's a closed, solid region. Its boundary is going to be a surface that's closed. Right? So I use this little symbol partial E to mean the boundary of E. So E might be a solid ball, and then its boundary is the sphere on the outside. Think of it as right? E is the orange, partial E is the peel, right, of your shape. The divergence theorem does exactly what that form of Green's theorem does. It says the net flux out of the boundary. Right? So this is a outward-oriented boundary. So we get the net flux out is equal to the triple integral now of the divergence on the inside. So like all of the big theorems we've seen in this class, it relates a sum of the change on the inside to a measurement on the boundary here. In this case, we take the sum of the divergence inside of a solid, and that's the same as the net flux right out of the boundary. How do you remember this theorem? Right, this is where I said think of it as like a conservation law. Well, one way, if you're a master of electricity and magnetism, you may already be familiar with this idea. Right? They've got Maxwell's equations. Right? We saw this on an example where the divergence is the charge density. That rho there is charge density. So it's the divergence of the electric field, right? How much it's spreading out, right? It's exactly what the density is. All right, the charge density is the divergence of the electric field. When we integrate these things, right, so you can integrate both these sides. Well, if you integrate charge density, you just get total charge, right? That's what happens when you integrate densities. You get the total of whatever the thing is it measures. So if I integrate charge density, I get charge. The divergence theorem says, well, if I integrate divergence, I get total flow out. I get the total flux out the boundary. And so right, Maxwell's equation becomes Gauss's law. The divergence theorem is also called Gauss's theorem here, which says that when you integrate the flux of the electric field through any closed surface, you just get the total charge inside. Right? Doesn't matter. So if I've got a bunch of charges around, if I were to integrate right, around any charge in any shape I want here, if I were to measure the total flux of the electric field out here, I would just get right, some proportion to the charge. There are some constants around. Right? That doesn't matter here. But the shape doesn't matter. So the flux through this shape would be the same as the flux through this shape here. And the flux through this shape is going to be zero. There's no charge inside here. Right? So whatever comes in goes out for the electric field there. Right? And so right, that's one of the natural results of the divergence theorem, right? Is Gauss's law. Now, some of you may be less familiar with Gauss's law. Let me delete that. And so maybe that's not the best way to do it. Although I do encourage you to get the slides here. This one is taken from a game a student pointed out to me, electric field hockey. It's a neat little application here where you try to score, but instead of using a stick, you just have electric fields. You can print some electrostatics that will push it around. Neither here nor there. So maybe E&M's not your cup of tea. How can you remember the divergence theorem? Right? I said it was a conservation law, like something's conserved here. Well, all you have to do is think about champagne. Now, this is a site maybe familiar to many of you, at least in general, right? That the Mets are celebrating is a little more rare here. But here's Terry Collins, 2015, celebrating his winning the National League pennant here. And what's he doing right here? So it's pretty clear that Terry Collins understands the divergence theorem. Why is that? Well, he's got all the ingredients. What has he done? He's taken a bottle of champagne, right here, the glass of which forms a surface, right here. If we consider the opening, right, just as part of our surface, the little cap over it, we've got a closed surface. Inside we have champagne. In there is dissolved a bunch of carbon dioxide. You agitate it, right? The molecules get together, they form bubbles, they expand. You suddenly have positive divergence, all right? So you got positive divergence on inside, right? The champagne fluid is expanding. Now, what does the divergence theorem say? It says, well, the total divergence on the inside has to be equal to the flux heading out, right? Right, that's what the divergence theorem says. So what's he doing with his thumb there? Right? Terry Collins is awfully clever here, right? Again, understanding the divergence theorem, he's not going to affect the divergence on the inside, right? That's just determined by the agitation and how carbonated it was and so on, right? What he's doing is changing the surface through which there's positive flux. Through the glass, there's no leakage, right? It's not breaking. So the only flux is out the little hole at the top, all right? Now the total flux is fixed again by the integral of the divergence on the inside. But if you make the area through which it can flow smaller, what has to happen? Well, the velocity of the flow has to go up out of there. And so, right, simply by manipulating that surface, right, Terry Collins has done his integrals. He knows that the champagne is going to spray a whole lot farther, right, into the crowd and be more celebratory. Right. So you can almost think of it as like, it's a conservation, and whatever's produced on the inside, meaning divergence, right, spreading out there, has to escape somewhere. Okay, what's a more mathy justification for this? Although I think the champagne is still kind of almost a better way to understand the divergence theorem, but we need to do, right, at least see a little bit of where the math comes from to have this make some sense. And I won't do a formal proof because there's a lot of details to get in with estimates and inverse function theorems and implicit function theorems maybe as well. But just to see where does this result? Why divergence on the inside is equal to total flux on the outside? We can do it with a fairly simple picture. So here's the general, right? The general picture. I've got a closed surface, weird distorted pepper kind of shape. Here I've got a vector field, right, flowing out, right, through here. And so the divergence theorem says that the flux through the boundary of this thing must be equal to adding up the divergence everywhere on the inside, right? So how does the inside sort of affect the outside here? Well, the way to do it is to chop this whole solid region, so the inside of this pepper, up into little boxes, right? Little regions. And you know that if you chop it fine enough, we can approximate this region with a bunch of small boxes. So let's zoom in here slowly and imagine that this vector field continues to the inside of this picture. And we'll look in at one little box all the way in the middle there. You can see it coming into view. Right. taking a little while to render, but you see it coming slowly into focus here. And so the idea is, instead of talking about the flux just through the outside, the clever bit is that if we chop it up into little pieces and measure the flux through the boundary of each little piece here, we're actually going to get the same answer. Why? Because if I only look at the flux through this little piece, but then remember there's another one stacked directly on top of it. And so where the two boundaries line up, those two flux computations are going to cancel. Right? The flow out of this little box on top is exactly the negative of the flow for the next little box above it, right? For the bottom of the next little box above it, right? They share this little piece. And so on the interior of my space, when I chop it up into little boxes, all the interior surfaces are going to cancel exactly, right? The flow out of one little box is the flow into its neighbor, right? There, and that makes sense. Where would we get something that didn't cancel? It's exactly when one of the sides is one of the boundaries of the whole surface, right? So the flow out the boundary that has no neighbor, right? That's the one that sort of counts in the net flux through the whole picture here, right? If this little box were on the outside here, right, it would have no neighbor to cancel. But for all the little pieces on the inside, they will cancel. So that justifies the following picture, that the total flux is basically a sum of all the little fluxes. It's a delta flux there, right? All the flux through the little boxes here. So let's just compute what delta flux is. What is the flux through a little box? And we want to use little because we can approximate things. We know that on a small scale, we have good approximations using linearization here. So I want to approximate the flux through this little box. So how am I going to do it? Let's just look at one side at a time. Let's just think about flux out these two sides here, right, for the fixed x value. So out over here, right, and in the back down here. So let's say the point in the middle, right there, that's going to be the point x, y, z. All right. You can imagine they're fixed for now, and of course we're going to add it up over the whole region here. But that's the point right there in the middle. And then we've got the size of the box, right? We've got delta x in the x direction, delta y in the y direction, and delta z, of course, in the z direction here. So I've got this little rectangular prism. It's a cube. If these are all equal, and I want to measure the flux out of this cube by my vector field. Well, if I notice on these two surfaces here, the only component that flows out, or the dot product, right, the only part of the dot product that gets preserved on these guys, right, that I highlighted, is just the first component, right? It's just the part pointing here, right? There's the normal vector n in the front, and it points out here, right, in the back, right? The unit normal vector out from here. And so my flux here, at least through these two surfaces, is just going to be given by the difference in the I component of my vector field. In other words, the difference of P at the front and at the back of there, right? Remember, my vector field here, I'm using the terminology that it's P times I plus Q times J plus R times K. So for the two surfaces I highlighted, right, Q and R don't come into it. It's only P that matters. So I'm going to find P at this point times delta Y times delta Z, right, minus P at this point, because now N points the opposite direction, right, here, times delta Y times delta Z. So I've got it here. So the delta flux just in the x direction, so that's what I mean, through those two sides perpendicular to the x-axis here. So that's the piece of the flux in the x direction is given by P at x plus delta x over 2 yz. Right? So that's just the middle of the one side minus P at the back side over here. Right? So I go up delta x over 2 to reach one side. I go back delta x over 2 to reach the other side there. So these are scalars. I take their difference times the area, delta y, delta z. That'll give me the different flux. But then I look, wait a second, this is a scalar value function at two different points right here, where y and z are fixed. So I can just use, I can use a bunch of things, linearization, the mean value theorem, even a couple ways of looking at it. This is approximately just the x derivative of p, right, and the middle there, times delta x, right? These 2 points are delta x apart. I multiply by the rate of change in that direction there. And so I keep delta y, delta z, and you're not surprised to think that the flux in the x direction, it's just going to be the x derivative of p, or approximately x derivative of p, there, times the volume of the box. And already we've related now, right, flow through the side to volume already, right? And you can see, and you can probably guess how this game is going to play out, right? In the other two directions, it picks off exactly the other components, right? The y derivative of q, the r derivative of z. You can make this analogy go through very quickly. Add them all together, right? Add these three terms, right? The flux in the three directions, right? Remember, my cube has 6 sides. I add up in 3 pairs there. I literally just add the flux for all, right, for all my sides together, right there. And now I have my, well, the ugly expression there. Why didn't that make that look nicer? The total sum of all the fluxes, it's just the sum of px plus qi plus rz. Well, you know what that is. That's the divergence of f dv. Right. Remember, divergence is the scalar. So this expression at the end here makes sense. It's just a triple integral of the scalar divergence of f integrated over the volume. This is not a fancy object. It's the same triple integral we've been studying before, right? It comes from a fancy concept of a divergence, but it's just a scalar integrated over a solid region, right? All right. So here's the divergence theorem again, right? So it says the total flux out of a region, so that's a surface integral of a vector field through the boundary, is equal to the triple integral on the inside of the divergence. Right there you have it. We'll do lots of work and lots of examples to hopefully, right, solidify these ideas. See you in class.